All right, let's get started. Hello, everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Mastandrea, and I am the Assistant Project Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful panel presentation today on interstellar dust grains, galactic messengers, and after the presentation, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentation, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe Study and for information on future webinars, please visit the Interstellar Probe Study website. And now I'd like to introduce today's speakers. Pontus Brandt is a space physicist at the Johns Hopkins University Applied Physics Laboratory, with research interests in space plasma environments, especially regarding the interaction of the solar wind with planetary systems. Pontus has held many leadership positions, including being the PI of the Jovian Energetic Particles Investigation Instruments for JUICE, and is the project scientist for the Interstellar Probe Study at APL. Verlie Sturken is originally from Belgium, studied aerospace engineering in the Netherlands, and did her PhD on cosmic dust at the TU Braunschweig in Germany, while being a guest at the Max Planck Institute in Heidelberg. After her PhD studies, she moved to Switzerland, where she was a postdoc at the International Space Science Institute. Now, she is a senior research assistant at the ETH in Zurich, focusing on simulations and measurements of the dynamics of the interstellar dust particles that move from the local interstellar cloud through the heliosphere. She kicked off a major project in 2020 on this topic, supported by the European Research Council. Bruce T. Drain studies the interstellar matter in the Milky Way and other galaxies with a focus on the physics of interstellar dust. He also works on the optics of small particles. A professor at Princeton University, he is the author of the textbook Physics of the Interstellar and Intergalactic Medium and a member of the National Academy of Sciences. And now, Pontus, the virtual floor is yours.
Thank you very much, James. So as usual, I'm going to set the high-level stage here for about 5 minutes to talk about what an interstellar probe really is. So an interstellar probe would go farther and faster than any spacecraft before, with the primary goal to explore the boundaries of this vast magnetic bubble, the heliosphere as we call it, that actually harbors pretty much the entire solar system that we live in. So these unique interaction mechanisms are responsible for upholding this boundary of the heliosphere is also applicable to a whole other vast range of heliosphere or bubbles around other stars, or astrospheres as we call them. And as such, it sort of represents one of the most outstanding problems in space physics today. Once beyond our heliosphere, the probe would begin its journey through the unexplored territories of interstellar space. Here we become the first mission to sample the changing interstellar clouds that our sun is plowing through. And it's a completely new territory that is decisive, not only for the heliospheric interaction in large, but it actually also holds the key for understanding the chemical evolution of the galaxy, which is part of what we're going to talk about today. On its way out, there are, of course, a whole slew of groundbreaking opportunities also for astrophysics, planetary science, including flybys of 1 or 2 Kuiper belt objects. And for the first time, it would also capture the large-scale distribution of the so-called circumsolar dust disk, which is a fossil record of how our solar system formed and evolved. Beyond this obscuring dust disk, the infrared spectrum would also gradually uncover what we call the extragalactic background light, which is a very important measurement in astrophysics that would provide us insight to early galaxy formation back to about 200 million years after Big Bang. So as you can see here in the little box over to the second box over to the left here, interstellar dust, as you will see today, is one of those science areas that don't really care about any of the disciplines that we're trying to stovepipe it in. And so in regards to this study, we'll soon be in our final year here at APL. It's a trade study where we'll look at the pragmatic solutions for an interstellar probe. With a nominal design life of 50 years and making launch in the 2030s a real possibility. So together with the Marshall Space Flight Center office, We've looked at about a dozen or more launch configurations and showed that asymptotic speeds of more than twice that of Voyager 1 can be achieved with conventional means. So let's go to the next slide. So interstellar dust, you'll hear much more about this today from the experts, of course. So interstellar dust originates from stars throughout the galaxy. So that's why we like to call it the galactic messengers of sorts, because it holds the clue of the chemical evolution. The whole challenge, of course, is that the heliosphere, it's a magnetic boundary, the interstellar dust grains are charged, so they will be deflected. So one thing we don't know is, of course, if the solar system dust is different from that of the interstellar dust, which is also important for understanding solar system formation. So to reiterate again, interstellar dust is therefore agnostic of science discipline, and they really span across all of the science goals that I showed from the beginning. Next slide, please. So as James said, we have two excellent speakers today. We're very proud to have them here. It's Dr. Bruce Drain from Princeton University. And I like to say this, he's the guy who wrote the book on the subject, or a book on the subject, as he liked to say. And of course, Dr. Verlis Sturken from Zurich, who is a world expert in simulating and understanding how this dust really interacts with the heliosphere. So without further ado, Dr. Drain, next slide, please. The floor is yours, and engage.
Thank you very much, Pontus. So I'm going to try to make this very brief, a few things about interstellar dust, where we stand in our understanding of them, and end up with what Interstellar Probe might be able to teach us about them. So we live in the interstellar medium. The solar system is moving through the interstellar medium. We think it's relatively well mixed, and so it's reasonable to presume that the dust now entering the heliosphere as we plow through the interstellar medium should be typical of dust in the diffuse interstellar medium. But that's an assumption. We don't know that to be true. So I will tell you a little bit on what we can say about dust in the diffuse interstellar medium from astronomical observations and modeling of those observations. These observations have recently led us to need to revise our thinking about what a typical interstellar dust grain may look like. And finally, I'll conclude on what Interstellar Probe may be able to tell us. Next slide, please. So I could spend hours showing you eye candy of interstellar dust, how it makes the galaxy and the universe beautiful. I'll restrict myself to one image here. Here's an image showing interstellar dust, both in its roles as an obscuration. So this is an image of a dark cloud blocking background starlight. You'll notice the deficiency of background stars in around this bright central object. The bright central object is a recently formed star that formed out of this cloud. And the diffuse light that you see is actually light that has been scattered by dust grains. It's not emission from the gas, it's light scattered by dust grains, light originating in the star. So we can study interstellar dust in a region like this through observations of scattering, through observations of extinction. And if we had our infrared eyes turned on, we could look at the emission from this region as well. So that's the kind of information that informs us about the optical properties of interstellar dust. Next slide, please. So where do these grains come from? So it has been, we know that dust is formed in outflows from stars. We see it. There are two classes of stars chemically, the ones which are oxygen rich, that's normal abundances. Those stars, when we study the dust that's formed from those which are capable of forming dust, tends to show evidence for silicate features. There are some stars where the atmosphere is carbon rich. You don't form the silicates, you do form silicon carbide and other forms of carbon dust. So we know these happen around stars, we can observe it. In addition, some supernovae we know make dust. We see evidence of dust forming in ejecta from supernovae. And in such a case, you might expect different materials to form in the zones with different with elemental enrichments from nucleosynthesis in the supernova. However, in addition to these so-called stardust grains formed from individual stars, you can also expect to be able to grow solid material in the interstellar medium. We have cold surfaces, we have gas atoms coming down and condensing on those cold surfaces. They are going to grow solids. In my opinion, This is the mechanism that's responsible for most of the solid material in the interstellar medium, but I can't lead you down the arguments that lead me to that conclusion. But it is controversial. So there will be some people who will tell you that they think the typical dust grain will be a stardust grain. I would tell you on the contrary that I think stardust is a small minority of the grains, that most of the grain material is made in the ISM. So next slide, please. We can study the composition of the gas of the grains that are in the ISM by looking at the elements that are missing from the gas phase. We think we have a pretty good idea about what the overall elemental abundances of the interstellar medium is, and we notice that elements like magnesium, silicon, calcium, iron, nickel are largely absent. There's small amounts of those elements are in the gas phase, but much less than we expect, and it's reasonable. The only reasonable inference is that the missing elements that are removed from the gas, the missing atoms, are actually in solid dust grains. So through spectroscopic observations, we have reason to think that the magnesium and silicon are primarily in amorphous silicates. Some of the iron is probably in amorphous silicates, but much of the iron is in forms that are still chemically unidentified. Maybe 25% of the oxygen in the interstellar medium is incorporated in silicates and oxides. And about 40% of the carbon is also in solid form in various kinds of carbon compounds. One material that you might have thought would be an abundant component of interstellar dust would be water ice. It's easy to form, there's plenty of oxygen, plenty of hydrogen, but in fact, in the diffuse interstellar medium, ultraviolet radiation appears to prevent the accumulation of water ice on grains. So we do not see any evidence of water ice on interstellar grains in the diffuse interstellar medium, such as the regions that the solar system is now moving through. Next slide, please. We can study the properties of grains as a function of wavelength and thereby get spectroscopic clues to what's in them. I can't talk very long about this, but this is showing the extinction as a function of wavelength plotted against 1 over wavelength. So high frequencies are on the right, long wavelengths are on the left. And going from the far ultraviolet down to the infrared, we see a general increase of extinction as a function of photon energy, a strong extinction bump at about 2200 angstroms, 4.6 inverse microns. That's probably due to aromatic carbon. And as we move into the infrared, that little inset, that's showing strong extinction features at 10 microns and at 18 microns that are due to silicates, and an additional small feature at 3.4 microns due to the carbon-hydrogen stretching mode. So these are clues to what the interstellar grain material is. Again, I could talk longer about this, but let's move to the next slide. Now, in addition to the elemental composition of the grains that we infer from the elements missing from the interstellar medium, from the gas phase, in addition to the spectroscopic clues for the grain composition that come from studying the wavelength dependence of the extinction, we also have information from the ability of dust grains to polarize starlight. So this was discovered serendipitously by Hall and Hiltner in 1949. So the idea here is that we have light coming from stars, typically unpolarized. It's only rare kinds of stars that are appreciably polarized. As that light passes through the interstellar medium to our telescope, if we observe it with a polarizer, we discover that typically the light reaching the telescope is linearly polarized. And that happens because it's traveling through an interstellar medium where the dust grains are, first of all, non-spherical, but also they're substantially aligned with their short axis tending to be parallel to the direction of the magnetic field. That's our current inference as to what must be going on. So this is an established phenomenon. We can study it as a function of wavelength, next slide, please. So we can study it as a function of wavelength. We observe it's very strong at visible wavelengths, tending to become weak in the infrared, but the wavelength dependence informs us about the sizes of the particles that are responsible for this. And so we conclude that we can make models that reproduce both the wavelength dependence of the interstellar extinction and the polarizing ability of the grains as a function of wavelength. With a grain model, it has a suitable size distribution and it has a suitable grain shape, where the grain shape has to be quite non-spherical. So as an example of the least non-spherical shapes you can get away with, maybe 1.4 to 1 oblate spheroids would work. if you assume that they're extremely well aligned. So there has to be an alignment as a function of size. For reasons that we're not certain about, the very small grains are not aligned, but the grains that produce the visible and the visible extinction and the infrared extinction tend to be well aligned. Next slide, please. Now, those grains that are aligned and producing extinction, they're also radiating energy. They're absorbing starlight energy. They're getting heated up. Where does the energy go? It gets predominantly radiated away in far infrared and submillimeter radiation. And if the grains are non-spherical and if they're not randomly oriented, that radiation is going to be polarized. So this is something which we expected from the early days of thinking about polarized dust, that the radiation from them must be polarized. But it's only been in recent years that we've been capable of measuring that the polarization of that emission. Because it's weak, the emission is, well, the emission is actually not weak, but our detectors have not been sensitive enough to do this until recently. So next slide, please. So now the Planck satellite has given us fantastic observations which force us to rethink our modeling of interstellar dust. So these are 4 images, all sky images produced from Planck data. The upper left image is the total intensity of radiation at one wavelength, 850 microns. This is in galactic coordinates with the galactic plane along the equator, the galactic center right at the center of the image, and you see that there's a tendency of the dust, the emission from the dust, to be very strong in the galactic plane, but to be easily detected up to the highest galactic latitudes. The image on the upper right is the polarized intensity at this same wavelength of 850 microns, plotted over the sky. We see plenty of emission along the galactic plane, but the polarization is very prominent in regions above and below the galactic plane. So we're detecting this with high signal to noise. Now, if we take the ratio of the upper right image divided by the upper left image, we get a fraction, the fractional polarization of the emission. That's the lower left image here, the fractional polarization. And the stunning thing that Planck has taught us is that in large regions of the sky, the fractional polarization gets up to values in excess of 10%, easily getting up to values as high as 20%. That's a real challenge for grain modelers to achieve that high polarization fraction, but we can do it. Along the way, Planck, from the direction of the polarization, can make a map of what the direction of the magnetic field is over the sky, and that's the lower right-hand image here. Next slide, please. Now, Planck has done those observations that I showed you. I showed you images at 850 microns. Planck also made similar maps at 5 other wavelengths, going to longer wavelengths. And in addition, we have observations from balloons, from a balloon experiment called BLASTPOL, which has carried out similar observations on a smaller area of the sky, a smaller and brighter region of the sky than the all-sky observations by Planck, but carrying out the measurements down to shorter wavelengths. And the fractional polarization as a function of wavelength turns out to be nearly constant, from 200 microns out to 2 millimeters. Now, next slide, please. That near constancy turns out to place serious limitations on grain modeling. I talked about initial thinking that there might be grains that were carbonaceous grains, might be silicate grains. If both of those types were abundant in the interstellar medium, they'd each be contributing to the far infrared emission, and they would likely have different wavelength dependencies of their infrared emission because they're different kinds of material, and they'd likely have different degrees of fractional polarization. And the net result would be that the fractional polarization would not be constant with wavelength. So this observation that it's nearly constant with wavelength out to, over at least a factor of 10 in wavelength leads us to think that the emission must be dominated by a single component. Next slide, please. So that's our current thinking. In the old days, we in fact had models that used two or more types of grain to reproduce what the observations are. But now we're forced to try to have one dominant grain type that has all of the elements that are missing from the gas within those grains, a size distribution appropriate to reproducing the extinction and polarization. And here's what the composition would look like. So we would expect that the grains would have magnesium to silicon ratios of something like 1.2 iron to silicon ratios of something like 0.6 based on the elements that are missing from the gas phase. Now, what do we know from observations on the Cassini, the cosmic dust analyzer in Cassini? Well, those elements actually look like the average for 36 grains measured by the cosmic dust analyzer. In the case of carbon, we don't know the answer because the cosmic dust analyzer had difficulty with carbon contamination and so wasn't sure about what the carbon composition of the grains was. Next slide, please. Okay, so this is my final slide here. I want to just summarize our thinking and lead you into Verley's presentation. The interstellar grains are arriving at the outer heliosheath at a velocity of something like 26 kilometers a second. The grains are typically charged. The small grains end up being filtered or having their trajectories deflected by the magnetized solar wind. So by the time you get to the inner solar system where all of our observations have been, where inner includes out to Jupiter, only the large particles have been able to arrive without significant deflection. Interstellar Probe, of course, by being able to measure it within the heliosphere out to much larger distances and then get beyond the heliosphere and beyond the heliosheath, we will have the opportunity to sample the interstellar grain population without this filtration and to determine directly what the abundances of the particles are if we have a dust detector on it. So I very much hope that there will be a dust detector. You will be able to discriminate between different grain models. Just mention here that some grain models have high porosity grains where you need to have larger grains to reproduce the optical property, the observed wavelength dependence of extinction. And so such a model would predict relatively high impact masses for the grains, whereas compact grains would have smaller masses per grain. So that's something that just measuring the mass of the impactors would be able to tell us. And of course, if we can measure the composition of the impactors, then we can determine whether the grains are arriving with all of the different elements typically mixed together in single submicron grains, or whether some of the grains are silicate and some of them are iron and some of them are carbon. So Interstellar Probe will provide the ground truth by directly measuring the size distribution and I hope also the elemental composition of interstellar dust. Thank you very much.
Thank you very much, Professor Drain. And now for Dr. Sturken's talk.
All right, thank you for the invitation. It's a pleasure to do this. Next slide, please. Alrighty, so 75 years ago, right after the Second World War, people were actually worried when the first satellites were going into space because of the hazard that dust particles would pose to the satellites. And throughout the years, people have been doing research because of that. But the motivation has shifted slowly into the scientific interest into the dust in space. I hope in the future that we will go the opposite way around, so that we can start right now with the scientific interest, and that hopefully in the far, far, far future, we have to worry about the impact hazard. That means that I hope in the far future, we will have more missions like the Interstellar Probe to go further and faster out. Anyway, throughout all these years, we have been sending dust instruments into space and developing dust instruments. So we have a lot of experience of 50 years of heritage in order to be prepared for the next step out of the solar system. And these instruments have done measurements in the interplanetary space and have done a lot of really nice discoveries, like from comets and active moons, the rings of Saturn, airless bodies, and so on. Next slide, please. But there's not only interplanetary dust in between the planets, there's also interstellar dust in between the planets, as Bruce has already introduced us to. We are namely moving through a local interstellar cloud. Actually, the latest research, as you can see in the middle plot, is that we are perhaps or probably even already outside of that cloud. And the dust particles can help us give the answer whether we are outside or not. But we're moving through this cloud at a velocity of 26 kilometers per second, more or less. And as a result of that motion, the particles can get through the solar system. On the right, you see the heliosphere with its structure, and only 2 spacecraft have been outside already, but they didn't have a dust detector on board, even though they had an antenna that could pick up some signals. But still, we don't have really very good measurements of dust out there. And not all the dust particles can get through, as we have already said today. Next slide, please. So particles like that from interstellar space in the solar system have already been discovered. The first mission that discovered them was Ulysses in 1993, and it has been taking measurements over 16 years and has about 500 to 900 interstellar particles measured. And measured, that means their direction, the mass, and the velocity. Ulysses was flying in a plane perpendicular to the stream of interstellar dust, and that made it very good for such a measurement. Apart from Ulysses, also Cassini has measured dust, 36 particles, and even the composition of those particles. However, they were restricted to a size of up to 0.3, 0.2 micrometer because of saturation of the instrument, and it was near Saturn. Also, there has been interstellar sample return by the Stardust mission, and these were rather larger particles of 1 micron. So basically, this slide is showing you that we have a lot of measurements already in the solar system. I mean, with a lot, I mean a couple of measurements. And what I definitely want to say is that these instruments cause selection effects, and also the orbits of the satellites and the methods, they cause selection effects. For instance, the sensitivity, the relative velocity, there could be saturation, and there could be contamination issues like Bruce Drain has already told you. Also field of view and spacecraft attitude, so we have to take that into account. Next slide, please. But not only the instruments cause a selection effect, also the heliosphere causes a selection effect. And that's because of 3 forces. The first 2 are solar radiation pressure force and gravity of the sun, which will cause the particle flow to go into a steady state flow, basically. Gravity or gravitation force will focus the particles beyond the sun and cause a higher density there, whereas the solar radiation pressure force will basically push them away. So when we are flying with Interstellar Probe, probably going downstream, towards the tail of the heliosphere is perhaps not the best idea. I mean, you can still do it, but you would miss out a part of the particles, depending on the particle properties. The plot on the right shows you the orbit of the Stardust mission, and also that it has been sampling at 2 AU, so it theoretically could not sample particles with a ratio of solar radiation pressure and gravity bigger than 2. Last but not least, there's a Lorentz force. These particles get very charged. The smaller they are, the more they get charged. So the Q over M is the charge to mass ratio. And therefore, they will interact with the heliosphere magnetic field, and there will be an effect of that. Also, fluffy particles will have a higher charge. And that is a disadvantage because they could be filtered out, but we can also use it in our advantage because we can basically use the dynamics or studies of dynamics of dust in order to get to know something about the dust itself, but also something about the heliosphere. So basically the heliosphere is some kind of giant mass spectrometer or a giant fluffiness spectrometer, as you can call it. Next slide, please. So this shows you the dynamics of the dust in the heliosphere for the very, very small particles. On the left side, you see simulations of John Slevin of tiny, tiny dust particles that never will get in the heliosphere. There's one question: they might pile up at the boundary of the heliosphere, and so we have to get outside of the heliosphere in order to be able to measure them. The good news is that we expect a lot more small dust particles than we have big particles, so we can expect a lot more particles than the 900 that Ulysses has seen so far. Then the intermediate particles between 100 nanometers and 600 nanometers, they will be subject to a 22-year solar cycle dependence. So there will be a focusing phase where they focus towards the equatorial plane of the sun, and there will be a defocusing phase of these particles. Next slide, please. If we go to the smaller particles, there will be very particular orbits that they have that are almost not intuitively anymore. And these kind of orbits here that you can see on the left, then translate into densities that we wouldn't quite expect on beforehand. The big question is, of course, if they can get in the solar system, yes or no. On the right of the plot, you see a cross-section of the solar system with the flow of particles. On the very right is the focusing phase, and on the bottom is the defocusing phase. And what you also see is that even in the defocusing phase, there will be kind of a little bit of a focusing north and south of the ecliptic plane. So even if we go out of the ecliptic plane during the defocusing phase, if we point our satellite in the right direction, I mean the orbit in the right direction, we might still be able to measure something. Next slide, please. So this is a summary of the dust dynamics. The very large dust will just pass through the solar system. Actually, we don't even need to get out of the solar system, except that it's easier to distinguish between interplanetary dust. It's gravitationally dominated, and it could also come from other directions. For instance, particles that have been ejected by a protoplanetary disk and that have a large gyro radius because they are large. Mid-sized dust will reach the inner solar system, and we can measure them probably also here, but it depends on the phase in the solar cycle, and they're subject to the three forces. Small dust might be reaching the solar cycle, but we're not sure about that. The solar system, but we're not sure about that. And they are Lorentz force dominated. And then finally, nano dust, there's no chance to measure them here. We have to get outside, and they might pile up at the boundary. Next slide, please. So Ulysses has shown us a lot of interesting data. And here you see on the bottom, the flux of the data of the interstellar dust particles, and on the top, the rotation angle, which is basically the direction that the particles are coming from. In color, you see some simulations for different values of solar radiation pressure force, and we did it for different charge to mass ratios. And we could either simulate the last part of the data or the first part of the data, but never the two at the same time. Next slide, please. And what we think is that that is because perhaps we have to find out, because we have simulated only the inner part of the solar system up to, let's say, the termination shock, up to 50 AU from the sun or 70 AU from the sun. What we still need to do is to simulate also how the particles get through the heliosheath, and that is a very unknown region in the heliosphere. This is a project that I'm working on now, which funnily also has the name Astrodust. And the interesting thing is that we try to learn about the dust, but using the dust, we can also, or using the measurements of the dust, we can also learn about the heliosphere. So the dust can be used, once we have an interstellar probe with these measurements, the dust can be used as a constraint to put on the heliosphere. Next slide, please. This is the mass distribution. On the left, you have the number density, and on the right, the mass distribution from Ulysses data. And there is a discrepancy between the astronomical data and the Ulysses data. So we have the filtering effect for the small particles, and we have measured too many big particles. What I want to show with these plots is that on the left side, you have the number density. We expect a lot of small particles. And on the right side, you have the mass distribution. Most of the mass is actually in the big particles. Next slide, please. So the science question, this is actually where it gets really interesting. The science questions we will be able to solve with Interstellar Probe. So we can divide them into three parts. The big particles, that's especially interesting for the cosmic abundances to see if they fit or not to the abundances as we see them now. That's related to the enrichment of the particles throughout the ages, the galaxy. Then we have the mid-sized particles, which are especially interesting for the first 10-15 years of the flight of Interstellar Probe, especially for the dynamics of the heliosphere and the coupling to the heliosphere, and also to constrain the dust particle properties and the heliosphere dynamics. Then we have the nanodust particles, the particles in between, let's say 10 nanometer, or between the PAHs and the dust particles. What is in between there has never been measured before. So if we get out there, we will get a lot of new information that we never had before. So that's really interesting. We wonder what the composition is from very small to very big, and the morphology and so on. And this research will yield synergies between heliosphere and dust science, and also perhaps even plasma science. Next slide, please. Now, certain mission aspects. We have to think about the instrument selection, and we have to do that as a function of a science question. So do we want to focus on the small particles, the mid-sized particles, or the big ones? That might also depend on what trajectory we are choosing. I mean, these two things belong together. I think if we go down the tail, we might think about the big particles instead of the small ones. But if we go in any other direction, I think we should really focus on the very small ones, on the tiny ones. Then spinning or 3 axis also depends on the orbit. And then the next 3 bullet points, trajectory, the direction we are going to. So ecliptic plane or not, the trajectory if we're going into the nose direction or in the tail or sideways, and the launch year, these are all coupled together. What you see in the bottom plot is in green, the focusing phase of the solar cycle, and in red is defocusing phase of the solar cycle. And I put there the starting dates, 2031, for instance. If we start in 2031, then we will going sideways, perpendicular to the stream of interstellar dust. And we will be going at the beginning of the focusing phase of the solar cycle, which is good because the next 10 years, we will still be more or less in the focusing phase of the solar cycle. The longer we wait, the more we are in the defocusing phase, and the worse it gets actually. So in 2034, we will go in the tail direction, in 2038, we will go in the nose direction. And I wouldn't really go too much, wouldn't postpone it too much more anymore. Next slide, please. So what I would say is that Interstellar Probe is a golden opportunity for compelling interstellar dust research for several reasons. First of all, it offers a lot of synergies between different science disciplines, and that's a huge asset, I would say. Heliosphere, plasma, and astrophysics research work together hand in hand to discover more than you could discover on your own. Then small particles cannot get in the heliosphere. Once we are out there, we will be doing unexplored territory. We've never measured this before. That's great. Nanodust species, everything that's in between the nanodust and the bigger particles, that is new, and that is complementary to what the astronomers are doing over larger scale distances. Then is there a pileup at the heliopause or not? Where does the solar system nanodust reside? For instance, particles that are coming from the sun, nanodust, but also beta meteorites. How do they affect the outer heliosphere regions? We can simulate that, but we also need measurements of that in order to check the simulations. Is the plasma physics affected, yes or no, by the dust particles? Because they never have been taken into account. Then the small dust is orders of magnitude larger in number than the big ones, so that's good for us. If we go to the nose, we go into the stream, so we have a relative velocity of 60 kilometers per second. That's also good for the flux, but also for the chemical composition measurements. We will also be able to detect sizes down to 10 nanometer, and we will cover the whole solar cycle to do that research. Next slide, please. So I hope that I could convince you that this is really worth putting a dust detector on board of this mission. Thank you.
Thank you very much to our panelists, and now we're going to have our question and answer session. So the first question, why are PAWs called nanoparticles rather than large molecules, from Mike Ruttman? And we can send that to Bruce.
Well, I don't care what you call them. I mean, they are molecules, they are nanoparticles, all the same to me.
Okay, thank you. And then the next question is also from Mike Ruttman. Are there differences in dust grain properties between local interstellar cloud and in the high T bubble around where the LIC is? Also for Bruce?
Quite possibly. It's hard in the high temperature, low density regions, it's hard to study interstellar dust. So we know relatively little about the grains that are there. They don't contribute very much to the overall mass budget of the dust in the galaxy, and our ability to sense dust grains is typically more or less in proportion to the mass of the material that's out there. So they are likely to differ in the high temperature gas by having been affected by destructive processes. But aside from the inferences we can make by looking at the abundances in the gas phase and concluding that there must have been some grain destruction to restore elements like silicon and iron to the gas, we don't really know much directly about the dust grains. So I'd like to know more, but that's where we are.
Thank you very much. And the next question is from Tom Kermegis. How would the dust affect the width of the heliosheath? Verly, would you like to answer that?
So I'm not a plasma physicist, so I don't know if that does affect it. But what we do know is that in that region, there's a lot of exchange with, for instance, the neutrals from interstellar space. You have pickup particles and so on. So I can imagine, so basically if you have a dust particle that gets very small, it will behave just like a pickup particle. So I'm wondering if that, I mean, the dust has basically never been taken into the equation of the plasma physics. But this is a question for a plasma physicist, I think.
Oh, thank you very much. And the next question is for Bruce from Elena Pavornikova. Do we expect to see variations in the size distribution and composition of dust on scales of a few hundreds of astronomical units as Interstellar Probe travels from the heliosphere boundary up to 1,000 AU?
Well, I would not have expected it, but it's still an open question as to whether there may be processes which concentrate the dust grains in regions of that scale. So I would be surprised, but I would also say that we should be open to surprises. We just don't know. We've seen variations in the arrival rate of dust grains at the Ulysses probe, which can be interpreted through deflections by the time-varying magnetic field. But as Virlis said, those models don't completely reproduce the data, so we should perhaps be open to the possibility that the arrival rate of the dust grains at the outer heliosheath may also be time variable because of variation, very small scale variations in the dust abundance. Although I must say, if that were true, I wouldn't know how to understand it. So it's a great question though, and the only way to know the answer is to measure it.
Thank you very much. And that's all the questions I see at the moment. So we can, if you have any questions from any of our attendees, if you have any additional questions, please post them in the Q&A feature now. Okay, I don't see any additional questions. So with that, we can go ahead and conclude this webinar. So thank you very much to all of our panelists. Oh, we just got one more question. I'll pause here, and it's from Ralph McNutt. How important would isotropic measurements be? And Bruce, and I'll let Bruce and Verley comment on this.
That should be isotopic measurements, of course.
Oh, sorry. Thank you, Pontus.
Well, so isotopic measurements would be very exciting. That would be a very good clue to the stellar origin of the particles or interstellar origin for the solid material. So I have no idea whether that's technically feasible. We of course do it when we study the interstellar grains that nature has trapped for us within meteorites. And so that's in fact how we recognize the grains, some of the grains in meteorites as being pre-solar because they are isotopically anomalous. So we know for sure that some of the grains in the interstellar medium today must be very isotopically anomalous because some of them are undoubtedly coming from individual stellar sources. But I would expect that the bulk of the material would not be isotopically anomalous because in my opinion, most of the interstellar grain material in the diffuse interstellar medium was solids that have reformed in the interstellar medium out of the overall isotopic mixture that's there. But that's something which, if we could measure the isotopic abundances, it would be fantastic.
Thank you very much. Verley, would you like to add anything?
Yes, at the moment, the current mass spectrometers have a resolution of about 200, 250. So it will be still a technical development to get to a higher resolution that we need, but who knows?
Okay, thank you. And the next question is from Michael Zemkov. Bruce, what evidence informs your opinion that dust is being made in the interstellar medium rather than in stars?
Well, that's a very long story. I'll try to summarize it. So I started off doing my PhD thesis on the evolution of interstellar dust. That was what I was assigned by Ed Salpeter, my thesis advisor. I thought about the grain formation problem a little bit, decided that was really hard, and after studying it a little bit, I turned my attention primarily to thinking about the destruction of grains in interstellar space, which had already been looked at by Michael Barlow and Joe Silk and others. And so I revisited that problem and came to a conclusion similar to what they came to, that the violent processes in the interstellar medium are pretty hostile to interstellar dust grains, and that if you put a dust grain out in the interstellar medium, it's not going to live the age of the galaxy. It's not going to live for billions of years before it finds itself in circumstances where it is destroyed by sputtering in the hot gas produced by a supernova blast wave. And so those considerations led me and others who looked at the same problem to conclude that interstellar grains wouldn't live more than a few hundreds of millions of years. Now, the problem with that is that even if you put all of the iron and silicon into solid particles when it left stars, if your grains are only going to live a few hundred million years, then most of the iron and silicon will end up back in the gas phase. And that clearly is not where it is. When we look for the iron and silicon in the gas, it's missing. 1% or a few percent of it's in the gas. The missing stuff is in the grains. So there must be some process to either we're completely wrong on how rapidly grains would be destroyed when they find themselves by chance in a supernova blast wave, or there's some process which reforms solid material and must be able to do so efficiently enough that most of the solid material would actually have been produced by that process. So that process is simply the accretion of atoms and ions from the gas phase onto cold grain surfaces, regrowing materials. Now, there's been a lot of argument about what material you would expect to form under those conditions. So I've told you that there's evidence for abundant silicate material. There are some people who think that this gas phase growth in cold conditions could not possibly make silicate materials, but in fact, even though the conditions are cold, there is ultraviolet radiation allowing modification, chemical, UV photolysis of solid materials that might end up producing silicates. And then in addition, there's been recent laboratory work where condensation in a low temperature situation has actually been found to be able to make silicate-like materials. So those are it's basically the lack of gas, of certain elements in the gas phase and the overall abundance of dust grains, which has persuaded me that there must be efficient generation of solid material in the interstellar medium. But it is a controversial issue as to just how important that is. And being able to measure the relative abundances of grains that are truly stardust versus grains that are this mixture of interstellar materials, materials produced in the interstellar medium would be very informative.
Thank you very much, Professor Drain. And then we have a question from Lynn Hillenbrand. It's actually no question, just high interest in anything more that the expert panelists want to convey. So we can start with Verly with a couple of minutes left. Is there anything that you would also like to briefly discuss that you didn't have a chance to in your presentation?
I'd have to think about that. I think no. I think actually most of the things I said in the presentation is that this is really worth it to put a dust instrument on board for several reasons, and especially the synergies.
Yeah, great. Thank you very much. And then Bruce, any additional comments that you would like to add?
Well, I'd like to come back to a mystery that Verly actually showed the data for. So the Ulysses probe measured the impacts by grains that by all indications were arriving on trajectories that were consistent with coming from the interstellar medium. Overall, the impact rate measured for the grains that had sizes of a few tenths of a micron, or therefore masses of 10 to the minus 14 or so grams, those grain, 10 to the minus 14, 10 to the minus 13 grams, the arrival rate of those grains was basically what we expected, particularly if you take into account the possible modulation of the arrival rates by focusing and defocusing by the magnetic field of the solar wind. However, the Ulysses spacecraft measured the impacts from much larger grains. The rates were not, the event rate was not very high, but the mass arrival rate was in fact high. So the Ulysses spacecraft reported detection of a mass flux in grains that were considerably larger than what those of us who model the interstellar extinction law would have thought at all likely. And so that was a big surprise. It continues to be a big surprise, because the abundance of the grains of the largest sizes, the abundance that Ulysses reported, I really don't see how that could be right. I don't see what could be wrong with the measurement, but I don't see theoretically how such grains could be present in a typical part of the diffuse interstellar medium. Now, it has to be remembered, we're sitting at one spot in the interstellar medium, sampling at one moment in cosmic time, and so maybe we're just sampling something that's extremely atypical. but that's a dangerous point of view to be taking. You know, our presumption ought to be that things that when we measure them are likely to be typical unless we have good reason to think otherwise. And so I'd like to see those Ulysses measurements confirmed, the mass flux of these large particles confirmed by another experiment that has been able to go well beyond Jupiter into the outer solar system. And if the mass flux is really there, then we have a real, people like me who model interstellar dust are going to have a real headache trying to understand it. Because in addition, there are two big problems. One is that when you make a distribution of sizes that accommodates the numbers that the Ulysses experiment was reporting, the resulting wavelength dependence of extinction just doesn't come out right. It doesn't, you can't reproduce the reddening law that we observe. In addition, the amount of material in these large grains that is required to reproduce the Ulysses data is an amount of heavy elements that just breaks our budget for what we think nature is providing in terms of the heavy elements abundance relative to hydrogen, since we think we know what the overall hydrogen and helium density is that's of the gas that we're moving through. So that's a big open question to me, and Interstellar Probe would be a great way to study it, and perhaps there'd be some tremendous surprise.
Thank you very much, Bruce. And Pontus, would you like to add anything else to this discussion?
No, not quite. I would like to give more time for the two questions that just rolled in.
Sure, absolutely. So the next question is from Mike Gruntman. How firm are estimates of the mass fraction of interstellar medium to be in dust? How variable is this fraction? Is dust in the sun's galactic neighborhood typical for the galaxy? Bruce, would you like to comment on this?
Sure. Well, we're not sure what the total abundances of the elements in the interstellar medium are, because they're hard to measure. Hydrogen we can study, obviously, but when we start talking about some of the elements, we measure them spectroscopically, and sometimes there's difficulties with making the spectroscopic measurements. So we're not sure about the overall abundances, particularly those elements which can be locked up in dust grains, where once you put the element in the dust grain, it becomes much harder to talk about how many atoms are there. However, a reasonable model is going to be that the abundances in the interstellar medium today are not very different from the abundances in solar sun-like stars that are being formed recently. We can measure the abundances in the atmospheres of those stars. They turn out to be not very different from the abundance in our sun, formed 4.5 billion years ago. So I think we know the overall abundances in the interstellar medium. And then we do have measurements from the ultraviolet where we see many of the abundant elements like magnesium and carbon and silicon being depleted from the gas, and therefore they must be in solid form. We can also infer the amount of heavy elements in the dust by trying to model things like the infrared emission from interstellar dust. Now those models are, everything there becomes model dependent because we don't know exactly what the grain materials are. But when we can make reasonable models with grain materials that have reasonable optical properties that can reproduce what we see using abundances that are like the abundance in the sun for the general interstellar medium around us. Now, some other galaxies do have very different elemental abundances. So in the small Magellanic Clouds, for instance, the abundances are well below the abundances in our part of the Milky Way. And we do have indications that the dust in the small Magellanic Cloud is quite different in its properties from the dust in the local part of our galaxy. I don't want to take up more time, so I'll stop there, but if there's a particular question, I could try to address it.
Thank you very much, Bruce. And I think we have time for one more question, and it's for Verley, and it's from Elizabeth Gavilan. Do you think that new measurements in the outer solar system could help constrain the origin of dust observed near the sun by Parker Solar Probe?
Perhaps constraining might be difficult, I don't know. I'm not sure how much we will measure there, and it might be difficult to go back to where they came from exactly. But it will be the first time, or the very first time, that we measure nanodust in that region of the heliosphere. So I think it will be mostly interesting for the dust solar wind coupling to do research on that part of the heliosphere. But I don't know, to go back might be possible. But
Thank you, Verly. And that's all the time we have for today. Thank you very much to our panelists, and thank you for attending today's webinar. Please visit the Interstellar Probe Study website for more information about the study and to view information on future webinars and events. Also, please consider signing up for our listserv under the community section of the website to make sure you're getting the latest information on upcoming webinars and events. Thanks for joining us, and have a wonderful day.